Hi, welcome to another edition of Fun with Conceptual Physics, the constant speed edition. The other day we gave you this handout and you should have it in front of you by now. I've returned them. And I want to go over some details. You'll also need an extra sheet of paper for taking some notes. In the back of the room is a stack of paper by the window if you need a sheet. If not, get open your notebooks. So I'll proceed. It says draw the motion diagram for a car that moves at constant speed. What constant speed means, and you're making oil drops, and you know the time between any two oil drops dropping from your car or dots being made, the time is 1 second no matter what the spacing is between them. Those marks are made every 1 second, like on the ticker tape machine you used. So if you move at constant speed, the distances between dots are equal. So if I make a dot here, 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 that might be vehicle A. If I have vehicle B, and clearly this is a time span of 0, 1, 2, 3, 4 seconds, and this is a time span of 0, 1, 2, 3, 4 seconds. If you want to make those marks, you can. So your first drop is like the start of a race. The stopwatch has not been started yet. Then the next drop is after the race is started. Then the next drop, or next mark. So both those objects, and this is object B, have moved for 4 seconds. But who's moved further? Clearly, the speed of A would be greater than the speed of B in this case because the spacing between the dots on vehicle B is smaller than the spacing between A. It's all about the spaces between the dots. So if you write anything down, spaces between dots tell you everything. The dots are made every 1 second. It's the spaces that tell you what it's doing. Now, when a car goes down an incline, what does it clearly do? It clearly accelerates. If you're accelerating, you're going faster. Therefore, and I'm only going to draw one vehicle this time, when you start out, your dots are close together, but they quickly start spreading out. So that should show acceleration. And why do you think it looks that way? The object gains speed, thus it accelerates. That would be a nice statement to know. So if you have your sheet, you can write that on there and see what I wrote. I wrote a statement. When you explain things, you have to give a statement that could have a period at the end, like a sentence. So I'm pausing for some kids to catch up. You over there, do you have a question? Oh, no? Okay. Make sure your cell phones are away. Thank you. Next, predict the motion diagram, what would look like for a car moving up an incline. Well, down an incline, all you do is accelerate. Does anybody know what happens to an object when it rolls up an incline and there's no motor making it move? Just an initial push? Yes, you over there. No, speak up. I couldn't hear you. Could you say it again? Oh, I didn't get that. No, over there, you in the green shirt. Okay. Yes, you're right. For an object moving up an incline, it's going to slow down to a stop. because it decelerates. So gaining speed is accelerating, slowing down is decelerating. What would it look like? If going up the inclines this way, it would start out traveling fast, but quickly slow down to a stop. So if you create a ticker tape down the ramp, your ticker tape should have looked like this. Almost a repeat of the first question, and since it accelerates, it speeds up, traveling, a larger distance each. Now print this out second. So if I hold that paper up there and get a different color marker, or these are felt tip pens, I don't know if I'd call them markers. In the very first second, remember this is 0 and that's 1, I traveled a small distance. A couple seconds later, or several seconds later, I'm traveling a huge distance. That's the indication that you're accelerating. That your distances, the spaces between the dots, is getting greater. Oh, I get that. So, if you made the ticker tape moving up the ramp, it would have started out going pretty fast and began to slow down rather quickly because the spaces get smaller. Since it decelerates, it slows down, traveling less distance each second. So there's the two. You can compare them using this just to hold that paper there. So you can see it's slowing down rather rapidly. In the first second it traveled a pretty big distance. By the last second, before it stopped, it was barely moving at all in 1 second. Remember, these dots are made every 1 second. Or in the same time interval. The time intervals between dots never changes. That's one of the homework check questions. The spacing does. So no matter if the space is big or small, it still took 1 second from dot to dot. I guess that's a good way to put it. From dot to dot, is always 1 second. So from dot to dot is always 1 second. The spacing, that's different. That can change because whether you're speeding up or slowing down or going at constant speed. Or you're going at a high constant speed or a low constant speed. Any questions over there? Yes? Oh, no questions? Okay, good. So, for example, if we look at car D here, this car is moving real slow because the spaces are small. Car A is moving faster because the spaces are bigger. But in both cases, the time between any two dots is always 1 second. Oh, that's cool. Give some people time to write those notes down. On the reverse side, we went through some of this. If there's any questions, I'll have this up here for a few seconds, and let me see if I can get most of this up here. If there's any questions on any of these, I could take it now, and I'll pause. Yes, what's your question? Oh, no question? Okay. And on the bottom, there was another one, in case you had a question on that one. Clearly, you can see the spacing's getting smaller. So this should be pretty straightforward. So at this point, I'd like to take a look at a couple of these problems. Read problem 1 to yourself. So here's some more practice today. And Steve throws a football and it travels 50 meters in 3 seconds. This is problem 1. Whenever you do these problems, it's good to make what's called a no-find table. What are you trying to find? It says right here, what is? This should be the easiest question because it's already right after the what. What is the average speed? What do you know? You know meters and you know seconds. You must have it clear in your head, units of distance or displacement. So your distance is 50 meters. I'll move my paper and your time is 3 seconds. Very few students ever have trouble with time units. But the units of time can be seconds, minutes, hours, and sometimes possibly days. Units of distance are meters, kilometers, and miles in this class. Notice I wrote MI. That is not miles. Kids are still messing that up. Speed or velocity, here's where it gets tricky. You can have units of meters per second, kilometers per hour, or miles per hour. As soon as a kid sees this M, they ignore the division sign and they think it's a distance. No, when these are together, it is always a speed or velocity. So the formula for speed is distance over time. And you clearly in this problem, does anybody have an answer? Yes, you over there? Oh, you need your calculator? I have calculators you can borrow if you'd like to come up and get one. You take 50 meters and divide it by 3 seconds, and I happen to have my handy calculator, my nice green one that I custom painted, John Deere green. It's a TI 83. Oops, and the batteries don't work, so I'll have to resort to one of the typical calculators we have, and I'll let you calculate it. So you take 50 divided by 3 and you would hit equals. The key thing are the units. So the answer is 16.67 meters per second. It's good to take these notes so you know what you're doing. So that's a warm-up problem. The next problem, Ashley takes 3 seconds. Does anybody know what the 3 seconds represent? Yes, you over there? What? I didn't hear that? Yes, you're right. It is time. At an average speed, it literally has the word in front of it. So this is not a distance. Your speed is 6.5 meters per second. What distance does she cover? On this one, we have to use an alternate version of the formula. So I'll make my no find table. No find on problem 2. We know the time is 3 seconds. Speed is 6.5 meters per second. And I spelled the words out. You could actually have this, meters per second, comma. You might have that, so be aware, it may look like that. What distance does she cover? Well, clearly that's what they want. So if I scroll back, I know this formula. You may want to write all three of these formulas down and know them. If I cross multiply by time, I get time times speed equals distance, or we usually write distance equals speed times time. This is the first version of our formula. This is the second version. And the third version is, do the Siever's flip, bring the S down and the T up. So I'm going to put the T where the box is, and the S where the circle is. Version 3 would say time is distance over speed. So you need to know all three of those versions and how to handle them. Remember, it's distance over speed. Well, I need time, or distance, so I can use this one. And it's pretty simple. Distance equals speed times time. The only thing you have to be careful of are the units. I have meters per second, and I have seconds. I don't have to convert, so I can just multiply. 6.5 meters per second times 3 seconds. These S's will cancel, and clearly my answer will be in terms of meters. So it'll be 19.5 meters. That's how far she moves. Give you time to write that down and look at that. It's very useful if you actually do the calculations yourself. So on the test, that's Wednesday, you can do the calculations. So Bart ran 5,000 meters from the police, it appears to be. Bart might have done something wrong. His average speed is 6.5 meters per second. So remember, it could look like this, and you'll have to recognize that it's 6.5 meters or 6 meters per second is actually a speed and not a distance. That is a speed. You have to stop and think. So if you have a no find table, and the distance he ran was 5,000 meters. His speed was 6.6 meters per second, that point, and he's looking for time. How long did he run for? How long is a time? So if we switch to the problem, and remember, we have three versions. Problem 1, use this version. Problem 2, this version. So we need time, so we're going to use distance over speed, and I'll let you calculate that yourself. So if you made your no find table, it should be pretty straightforward, knowing that you want time is distance over speed. The other version was distance equals speed times time, and then you have speed equals distance over time. Those are your three versions of the equation you need to know. Not entirely hard. Does anybody have the answer? Yes, you over there? Yes, louder, please. Again? And what are the units? Oh, the only units in the problem are seconds. So How many people agree with him? Looks like Bart ran for a time that was ridiculous because it's 5 kilometers. That's long. So it took him 833.3 repeating seconds. Or if you want to divide that by 60, he ran for 13.89 minutes. Clearly, there are 60 seconds in an hour. If you divide this by 60, you'll get minutes. Well, there you have it. There's some good practice and notes. And we're going to segue into a graphing thing now.